So go ahead and draw this wheel, and let's say that the wheel spins for 5 radians. Go ahead and draw on the wheel itself how much that is based on, the radian measurement there. So yeah, go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so remember the arc length here is this arc length is the same as the radius. So the radius length is the same as arc length. That makes this angle here a radian. So we have 1 and then 2, 3, 4, 5. And remember, all the way around would be 6.28, which is 2 pi. 6.28 radians is, all the way around. And it's important to remember that intuition. If it takes 0.5 seconds, how fast is it going? So go ahead and pause the clip and do that. When you're ready to check, you can hit play. All right, so omega is how many radians per second. So theta over time, 5 radians in 0.75 seconds is 6.67 radians every second. So in 1 second, it's going to go, greater than a full, greater than a full circle all the way around. Because 6.28 is, all the way around, but this is going to go a little bit more than that in 1 second. All right, so the wheel slows down from 12 radians per second to 3 radians per second in 5 seconds. What is the angular acceleration? So as you work through these, I encourage you to get your equation sheet and work through these like this would be in the test and see if you can get it. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so angular acceleration is equal to the change in angular speed over time, and we should get negative 1.8 radians per second squared as the acceleration as this slows down. So during that time, how far did it go? How many radians did that cover? So if it started at 12 radians, went to 3 radians per second in 5 seconds, how far angularly did it go? So go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so we can use one of our kinematic equations. The final angular speed is 3, the initial angular speed is 12, and the acceleration is negative 1.8. So it should go 37.5 radians during that period. All right, so how far linearly? How many meters did it cover? And let's assume that this wheel has 0.5 meters. And so, or the radius is 0.5 meters. So go ahead and pause the clip and do that. When you're ready to check, you can hit play. All right, so if you remember, d equals r theta. So we have our radius times our how many radians we have. So it's going to go 8.75 meters linearly. All right, for this one, tire's going 75 revolutions per minute. How many radians per second is that? So this will be good practice here. Go ahead and pause the clip. Give this a try, and when you're ready to check, you can hit play to continue. All right, so remember when you set up your bracket, this is revolutions per minute. So 1 revolution, that means 1 full time around, is 2 pi radians, and which is 6.28 radians. And when we set up our bracket, we have the minutes on the bottom down here, so we need minutes over there, and getting that into seconds. So the angular speed is 7.85 radians per second. How many meters per second is the tire going if the radius is 0.75 meters? So go ahead and pause the clip and do that. When you're ready to check, you can hit play to continue. All right, so the radius is 0.75. The angular speed is 7.85, so this is going 5.89 meters every second. So in other words, that's how far linearly this is going to go during that every second. All right, so now let's take a look at angular acceleration, how that relates to linear. If you remember, you just multiply the radius by angular, and that will give you linear. And so, we set up first d equals r theta. And if we multiply the radius times the radians, we'll get the distance. V equals r omega, which is the radius times the angular speed, will give us linear. And now linear acceleration equals radius times the angular acceleration, and we can get the linear there, or vice versa. All right, so let's go ahead and take a look at this here. Let's say that we have a force on an object. It's good to practice how to do this. Remember, we draw a line from the middle, the axis of rotation out to there, and we can, let's say the angle is 28 degrees. What we need is this right here. We need the force that is, perpendicular to the lever arm. And so when we do that, we can set up our trig. Let's say it's 18 newtons. That side of the triangle is 8.75 newtons. So therefore, this length here, if it's 0.4 meters, this will be 8.45 newtons, and we'll get a torque of 0.338 newton meters. Now, the other way to do this, right, is if you apply force over the lever arm there, and let's say that length is 0.0188 meters, and we should get the same torque. And we've got that there. Now remember, with translational and rotational equilibrium, translational equilibrium is left, right, up, down. So that would be like, you got a car, you got a force applied this way, you got a force of friction this way, and let's say that you got a normal force and a force of gravity. Well, if everything is balanced, it's in translational equilibrium. That means it's not accelerating. So with rotation, let's say this is the axis of rotation in the middle, and let's say that, this is spinning. It's going around and around and around. And let's say there's no air resistance, no friction, it's just going to keep on spinning forever. It would be in rotational equilibrium. Let's say that there is a torque on it, right? Let's say that there's a torque this way. Well, if you apply torque this way at the same time, it's still going to spin, right? And so, or if an object is stationary and we apply a torque this way and apply a torque this way that's equal, it's going to stay at rest. So rotational equilibrium has to do with no net torque. Translational is no net force. It's important to distinguish between those two. All right. Now remember, with moment of inertia, right? We looked at the different objects. We were able to derive those. We first looked at a point mass, which is mr squared. Then we looked at what if you have two masses that are spinning, that's 2 mr squared. If you have a full ring, that's the mass of the entire ring times r squared. If you have a disc or a cylinder, it's 1/2 mr squared. If you have a sphere, it's 2/5 mr squared, and a rod is 1/12 ml squared. And the consistent thing here is, with moment of inertia, it has to do with two things. How much mass you have. The more mass you have, the more moment of inertia you have. And then also, the greater the radius, the more moment of inertia that you have. So when we look at kinetic energy, we look at angular kinetic energy or rotational kinetic energy. It's 1/2 I omega squared, and it'll come out to be in joules. And we can get, and the energy that way. So again, with moment of inertia, it's how hard it is to get an object to rotate or stop rotating. And again, there's two main factors. How much mass do you have? What's the radius? And the more mass you have, the greater radius that you have, the more moment of inertia that you're going to have. And so even if you look back at those last, pictures, you had that mass, that singular mass that was going around, and then you had the ring, and then you had all of that. The more mass that you have, the more moment of inertia it is, the harder it is to get that to either start going or to stop. And then the greater the radius, the harder it is to get it to move, to get it to rotate or stop. All right, so let's say we have this ring, and the ring's mass is 45 kilograms. The radius is 1.5 meters. And let's say that it's going 1.3 meters per second. What we want to do now is calculate the translational kinetic energy as well as the rotational energy, and then add them up to get the total. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so we should get 38.025 joules for the translational kinetic energy. That's 1/2 mv squared. For the rotational, it's 1/2 I omega squared, which is the moment of inertia for I. And the moment of inertia, we're going to need to also get the angular speed, so V equals R omega. And the angular speed is 0.87 radians per second, which we can get in there, and we'll get 38.318 joules for a total of 76.34 joules. And that should make sense because, you know, as this spins, it's moving translationally, but it's also rotating. And so we have both of those energies involved as it rolls. All right, so let's say we're spinning something around a fixed point. This would be like me holding that, that wheel in class and then spinning it. The further that you get from the axis of rotation, the greater the tangential speed. And so the closer you are to the middle, the less tangential speed that you have, the further you are out, the more you have. And now if we take a wheel and we don't let it rotate, but we slide it across the table, that's what this will look like, right? There'll be the same translational velocity at each moment. So when we bring those together, if you remember, what will happen is it's the combination of the two. So in other words, the linear, which is here, and the linear, which is here, will add up together. This is rotating, right? But up here, the tangential speed adds to this one to make it double. So this is double what it would be. But, you know, as this rotates around, the linear velocity here is going this way. And then as it goes from left to right, the velocity is this way. So when you add up this plus this, you get 0. And that's why it's still at the bottom. And that's why it's static friction. As a wheel rolls, it's still against the ground at every moment. And we've got that there. All right, so now we're ready to look at the object rolling down a ramp versus sliding down the ramp. You know, if we have you know, let's say this is a frictionless surface. If this just went down without rotating, then, you know, there's no rotational energy. It's just staying a fixed mass as it goes down. But if it is rolling, that means that the potential energy that we have up here not only is going into translational kinetic energy, which is left and right here, but it's also rolling, and that is energy as well. And so when we look at the full equation, non-conservative work, we have to look at kinetic energy translational plus kinetic energy rotational plus potential energy gravitational change plus change in potential energy of the spring. And so now we're adding to this equation the rotational energy that can be a factor here. So what I want you to do here is derive the equation for the system here, well, and actually figure out what V final is at the bottom. What's the final speed using non-conservative work? And this will be good practice for you here going back to do that. And when you're ready to check, you can hit play to continue. All right. So where our two unknowns is omega final. We don't know the angular speed that it finishes with, and we don't know the final velocity either, the final speed. And so we'll set up our equation. So there's no sliding friction, so non-conservative work is 0. There's rolling friction that's allowing it to roll, but there's no sliding friction. Therefore, it's not taking away any of that energy. And so we have translational 1/2 mv final minus 1/2 mv initial, and then plus 1/2 I omega squared, which in this case here we have in place of omega v over r, right? Because we know v equals r omega, and we can set the linear over the radius and get that. And then the final height is 0, the initial height we have, and the initial angular speed is 0. So that simplifies it there. Our radius will cancel out, our masses can cancel out, and we'll end up getting 6.26 meters per second. And this is less than what it was, you know, with just a block sliding down, because the block is not, you know, rolling at all. And as this goes, it's rolling at the end, and that's why it's so much more. All right, so it's also important to look at here what's going on with connected objects. Now, these are unique because we have two masses. We have the large mass here, and then we have the small mass here. Again, large mass, small mass. And so here we've got to bring those two together. We have a rotating thing going on here, and then we have a linear thing going on here. and then, we're going to bring those together. So what we're going to do is practice the derivation of this mass that's pulling on this wheel, or on this ring rather, and I want you to solve for the acceleration of this system, looking at both torque and what's going on linearly. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we've got the positive down, up is negative, and that's helpful as we look at the torque causing what's happening here. So negative force of tension plus positive force of gravity. Here, the force of tension is going to be positive, causing the ring to roll faster. And so we'll have positive there, and we're going to need to get our angular acceleration into linear. And then when we cancel the things out there, we'll get force of tension equals ma, which we can place in there. And our final equation should come out to be mg over m plus capital M being the large mass. All right, so let's say that we have a disk here, and we have a brake pad that is on this disk, and you can see it's quite hot here because that kinetic energy is turning into thermal as it slows it down. Let's say that the mass of the ring is 7.5 kilograms, and let's say the initial angular speed is 115 radians per second, and it's going to bring it to a stop. This brake pad's going to bring it to a stop. The radius is 0.16 meters. How much torque will it take to stop it if it takes 1.9 seconds? So this will be good practice with force and what's going on here with that. So go ahead and torque, and so go ahead and pause the clip. And when you're ready to check, you can hit play to continue. All right, so we've got that force causing it to slow down, and we know that torque equals I alpha, and we can figure out how much torque it takes if we know what the acceleration is doing. So we can look at what the acceleration is doing. That's the change in omega over time, or the constant acceleration equation. And we should get an acceleration of negative 60.5 radians per second squared, slowing this down. Therefore, because this is a ring, mr squared, we can solve for how much force it's going to take, or how much torque it's going to take. So the torque is 11.616 newton meters to bring this to a stop. And how much force would that be? So go ahead and pause the clip and calculate that, and when you're ready to check, you can hit play to continue. We get a force of 72.6 newtons for the force slowing this down, the average force. All right, so let's say we have a ball that's rolling down in an alley, and we want to find out how much work it takes to stop this ball. Well, in this case here, it's rotating, but it's also moving translationally. So when we're dealing with this, we need to work with, how much angular work would it take, and then also how much linear work will it take. And so let me give you the parameters here. The mass of the ball is 6.5 kilograms. The radius is 0.12, and it's going at 12.5 radians per second. What we're going to need to do is two different ones, right? We're going to need to deal with how much work it takes to slow it down angularly as well as linearly. So yeah, go ahead, pause the clip, and give this a try. And when you're ready to check, you can play to continue. All right, so we have the work equals a change in kinetic energy. The moment of inertia for a sphere is 2/5 mr squared, and so the moment of inertia is 0.03744, and we should get negative 2.925 newton meters as the work to slow this, or to stop this rotationally. Now translationally, we have the final kinetic energy minus the initial. The final is 0. The initial, we have to get into linear, which is 1.5 meters per second for the speed, so we can find the energy. And then translationally, it's going to lose 7.3125. So it's going to take a total of 10.2 joules to slow this down and bring it to a stop. So let's revisit this one here. How much work will it take to stop this disk as it spins? Now I want you to, instead of using work equals a change in kinetic energy, let's go ahead and apply this to the other work equation, which is dealing with torque and angular displacement. So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we can get the angular displacement, and that's 109.3 radians, and we know how much torque there was, and so we've got negative 11.616 for the torque, and the work that's going to take is negative 1,270 Newton meters. All right, so let's take a look at the snowboarder, and the snowboarder is in a jump and is spinning, and we want to find out the angular momentum of the snowboarder. So let's say that their moment of inertia is 430 kilogram meters squared, and let's say that they are spinning at 7.2 radians per second. Go ahead and pause the clip and calculate the angular momentum, and when you're ready to check, you can hit play to continue. All right, so L equals I omega, and we should get 3,096 kilogram meters squared per second. Now, let's say that his jump is 1/2 seconds long, and let's say that he ends up slowing down to 6.8 radians per second, keeping the same moment of inertia. Let's say that, his arms are pretty consistent here and legs, and so yeah, what is the torque slowing him down? So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. All right, so remember the change in momentum equals torque times the time. The change in momentum here is L final minus L initial, and so that's I omega final minus I omega initial equals torque times time, and we should get a torque of negative 344 Newton meters. Is the torque that slows him down as he spins due to air resistance. So a jumper, right, can adjust their body to make them spin faster or slower. And so if we look here, let's say a snowboarder is up in the air and decreases their moment of inertia by 1/4 by bringing her arms in during a jump. And let's say their initial angular speed was 2.6 radians per second. Let's figure out how much faster will they spin if they reduce their moment of inertia by that much, assuming there's no outside torque, that there's no influential torque causing them to slow down or speed up. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so the initial angular momentum should equal the final. And so therefore we have full angular speed times omega initial, and then afterwards we have 3/4 of the moment of inertia. It decreases by 1/4, so that's 3/4. And the question is, how fast will they be spinning? So if we set that up, we have the full I, and then a moment of inertia times 2.6, and then we have 3/4 of I, which we can divide both sides by 3/4. And we should be able to get our omega final, and they're going to be spinning faster at 3.467 radians per second.